Hi everyone, welcome back to my YouTube channel. This is Nehati from Sri Venkateswara College of Engineering, and today I'm here with a video on pointer aliasing and set associativity. So we'll be understanding the memory management and cache design in this. And first of all, what I want to say is that in this video we won't be dealing with these topics in depth. We'll just be saying a brief introduction about these two topics in this. So the contents are, we'll be seeing about pointers, then we'll see pointer aliasing an example, how it occurs and what are the possible risks it have. Then we'll be seeing about pointer aliasing in different languages, its detection and management. Then we'll start with the next topic, that is set associativity, cache operations and performance implication, and the conclusion. So, what are pointers? Pointers are nothing but they are the variables that stores the memory address, allowing for direct memory access and manipulation. So basically, what is a variable? A variable stores a value. It is a name memory location, and the memory address of this variable is stored as a pointer. So basically, pointers are memory addresses. Pointers are variables. Pointers are also variables that stores the memory address of a value. Okay. So now what is pointer arithmetic? Any operations we perform on the pointers are known as pointer arithmetic, like incrementing, decrementing, traversing an array, and everything of that sort. So what is point? We'll see the pointer declaration and initialization. What pointers are used to store the memory addresses of other variables, functions, or even other pointers. Okay, that is the definition of pointer. So here we have a variable. X, and its memory address is 2000, and it stores a value of 10. So the pointer PTR, it stores the memory address of the variable X. So what was the memory address? It is 2000. That will be stored in the pointer PTR. Okay, so that is what is given here. Int is X is equals to 10. Int star pointer, star is used for pointers. Int star pointer is equals to and %X. It stores the memory address of the variable X. So that is pointer declaration and initialization. So now what is pointer aliasing? Pointer aliasing occurs when memory location can be accessed through different pointer references. So what is aliasing? Aliasing is when two different expressions refer to the same object. That is what is known as aliasing. So your pointer aliasing means when a single memory location can be accessed by different pointer references. That is pointer aliasing. Now we'll read it out. Pointer aliasing happens when a single memory location is accessible through different symbolic names of the program. So we have a single memory location, and that can be accessed through different symbolic names in the program. That is when it is known as pointer aliasing. The name pointer aliasing applies to specifically accessing the memory location through pointers, although the same effect can be achieved when accessing the memory location through any references or any other way. This is about pointer aliasing. Now, for example, now here we have int x is equals to 10. Int star p1 is equals to x. Okay, so p1 is a pointer that stores the memory address of the variable x. Int star p2 is also equal to and %x. So that is also storing the memory address of the variable x. So if we change over here, we change any value over here, it changes in these two as well. That is what happens. Yes, the value is 10, variable is x, and the memory address of this variable is 0 into 100. Okay. So when pointer 1, that is p1, it stores the memory address of variable x. So the memory address of variable x is 0 into 100. So that is stored in the value, okay, for pointer 1. Same with pointer 2 also. But these two can have different memory address. That is the memory address of the pointer p1 and p2. But p1 and p2 stores the memory address of the variable x. So that is what happens here. Even if we change the value of 20, these two will have the same value. Okay. So that is example for pointer aliasing. Now, how it occurs and the risks and issues will be seen. How it occurs, aliasing happens when multiple pointers are assigned the address of the same variable or memory block. As we saw in the previous example, multiple pointers that are point P1 and P2 were there, but they're accessing the address of the address of the variable X. That is how pointer aliasing occurs. What are the risks and issues it has can lead to hard to find bugs and undefined behavior, especially in concurrent or multi-threaded programming. It will lead to it will there will be hard to find bugs that are hard to find. It will lead to can lead to hard to find bugs and undefined behavior, especially in concurrent or multi-threaded programming. That is the risk and issues it has. Now, pointer aliasing in different languages, we'll see. This is just a brief. C and C++, it is common due to manual memory management. In C and C++, it is manual memory management, and pointer aliasing is common due to it. Java, less common due to garbage collection, but references can still alias. Okay. Python uses references, so aliasing occurs with mutable objects. This is the how pointer aliasing is in different languages. Now, detection and management of this. Compiler optimization. Compilers can optimize code by assuming no aliasing, but this can be controlled using restrict keywords in C and C++. So what happens is compiler optimization basically says that in C or C++ language, it can use a restrict keyword to optimize code by assuming, it's just assuming that there is no pointer aliasing, and how it is by using the restrict keywords in C and C++. Techniques use of constant qualifiers, careful memory management and design patterns, tools, static analysis tools and dynamic analysis tools to detect aliasing. We can use static analysis tools and dynamic analysis tools to detect the alias. So this is about detection and management. Coming to the next topic, that is set associativity. Set associativity is a method used in cache design to determine how cache entries are mapped to the cache lines. So we'll be seeing about what is cache now. Basically, set associativity is how it is used to determine how cache entries are mapped to the cache lines. Okay, so that is set associativity. What is cache? Cache is a small, fast memory layer that stores frequently accessed data to speed up access time. So cache is a small and faster memory. It is faster than the main memory, and it stores a frequently accessed data so that it can speed up the process. So types of cache memory we have is L1, L2, L3 caches with varying speeds and sizes. Okay, now types of cache mapping. We have three types, that is direct mapped cache, fully associative cache, n-based set associative cache. That is also known as k-based set associative cache in few textbooks. So what does direct map cache? Each memory location maps to exactly one cache line. That is direct map cache. Fully associative cache, any memory location can be stored in any cache line. So first one is direct map cache, that in which each memory location is maps to exactly one. Each memory location maps to exactly one. That is directed mapped cache. In fully associative cache, any memory location can be stored in any cache line. That is fully associative cache. And n-way set associative cache, a compromise between the two, where each memory location maps to a set of n cache lines. That is why it is known as n-way set associative cache. Now, set associative cache operations. Cache misses and cache hits. First one is cache misses and cache hit. Explaining, we'll be seeing how data is searched in cache and what happens if it is hit or miss. We'll be seeing in the next slide, we'll be seeing about cache hit and cache miss. Replacement policies like strategies like LRU, that is LRU means least recently used, and FIFO is first in, first out. These are replacement policies. If cache miss happens, what happens is shown here, cache miss and cache hit. Then cache mapping techniques, how data is mapped to cache lines and different cache types. Okay, so that is the operations of set associativity. Now we have cache hit and cache miss. Okay, cache hit occurs when the data requested by the CPU is already found in the cache memory. If the data requested by the CPU requests the data, and if it is already present in the cache memory, it is known as cache hit. And what will be cache miss? It occurs when the data requested by CPU is not found in the cache memory. Okay, so that is cache hit and cache miss. Since cache memory is faster than main memory, retrieving data from the cache results in quicker access time. So cache is faster than main memory. So if it is already, when the data requested by CPU is already present in the cache, it makes it even more faster. Okay, so this speeds up processing and improves overall system performance. The higher cache hit rate, the better the system performance, because if it is faster, if it's already present in the cache, it is easier and faster. And so it leads to better performance of the system. Now it's opposite in cache miss. In this case, the system has to retrieve the data from the slower memory. So if it is not present in the cache, if the data requested by CPU is not present in the cache, it is known as cache miss. And if there's a cache miss, it has to bring the data from the slower main memory. So it takes time. Okay. So the system may also need to store the data in cache for future access. Cache misses can lead to delays and decreased performance. So minimizing cache misses is essential for optimizing the system efficiency. Okay, now these are two replacement techniques what we saw, LRU and FIFO. LRU is for least recently used and FIFO is for first in, first out. So least recently used is a cache replacement policy that replaces the data which has not been used for the longest period of time. So it is a replacement policies, and in least recently used in LRU, what we do is we replace the data that is not used for the longest period of time. If we didn't use the least used is the one that is replaced. That is for LRU. The idea is to track the usage of each cache entry and evict the one that was accessed the farthest back in time when a new entry need to be added. Okay, so when a new entry is going to be added, we replace the least recently used, that is for least recently used. This approach assumes that the data accessed recently will likely be accessed again and again soon, making it an effective method for improving cache hit rates. Okay, so what happens in this LRU is the data accessed recently. It assumes, okay, this approach assumes that the data accessed recently will likely be used again. So if it's frequently used, they assume it that it will be used again, so that it is an effective method for improving cache rates. Okay, so there might not be many hit rates. That is why we use LRU technique. FIFO is a simpler cache replacement policy that removes the oldest data in the cache when the data needs to be added. So as the name says, FIFO, first in, first out. So the ones that is already first in will be the ones to be out first. Okay, that is first in, first out. It operates like a queue where the first piece of data to enter the cache is the first to be removed. This method do not consider how frequently or recently data is accessed, making it easier to implement but potentially less efficient in maintaining frequently accessed data in the cache. Okay, so this is about the replacement techniques. Two replacement techniques we saw, LRU and FIFO. Now we'll be seeing about the performance implications, okay, of this set associativity. Set associativity in cache design improves performance. How? By reducing conflict misses, leading to higher hit rates compared to direct map caches. Okay. While it slightly increases access time due to searching multiple lines, efficient replacement policies like LRF help to manage data efficiently. So the replacement, it'll improve the performance by reducing misses and increasing the higher hit rates. And it also, how it does is by using efficient replacement policies like LRU, FIFO, etc. to manage data efficiently. This balance between the complexity and performance result in better system efficiency and a reduced miss rates. So this is about the performance implications of set associativity. Okay, now we have the case studies and examples. So in this, we'll see the real world applications. Some of the real world applications are processors like Intel and AMD, benchmarking and performance analysis, tools and techniques for measuring cache performance. Okay, so this is about set associativity. Coming to the conclusion, both pointer aliasing and set associativity highlight the importance of understanding low-level details in computer science. Okay, these concepts are fundamental in optimizing performance and ensuring reliability in software and hardware systems. The fields of memory management and computer architecture are constantly evolving. Staying updated with the latest techniques, tools, and best practices is essential for any developer or engineer working in these areas. So both set associativity and pointer aliasing that we saw in this video are very important in understanding low-level details in computer science. So in this video we just saw a brief of set associativity and pointer aliasing. We didn't go in depth. So if you all have learned something from this video and enjoyed this video, please do like it, share it, and please subscribe it. So we'll be winding it up now. Thank you everyone for watching it again.